Hello and welcome to lesson number, I believe this is 14. Is that correct? Yes, 14. All right, so welcome to lesson 14. Today we are going to talk about vectors. So vectors are mostly, you're going to find them in engineering and physics a lot. They can exist in other places, they can be used for other things, but those are the two places where they're mostly going to make their home. And we've talked a little bit about what vectors are from a math perspective, but today we're going to talk about kind of how they work from a physics perspective. So, a vector, vectors are measurements with magnitude and direction. So when we say that in math, magnitude just means it's a set distance, it's a set amount of space. But in physics, when we say a magnitude is a amount that is measurable. So, for instance, speed. You can measure someone's speed, but that wouldn't be a vector by itself. So, if you're going 90 miles an hour and you just tell someone, "Oh, I'm going 90 miles an hour," that's not a vector. Okay, that's a scalar. You're going that fast, but there's no direction given to it. Now, if you told someone, "Oh, well, I'm going 90 miles an hour forward," now they have a sense of direction. And the real reason this exists in physics is because there are forces that act in addition to each other and against one another. So let's go ahead and go to the board and give you an example of what I'm talking about here. In physics, they use these a lot. They tend to call them free body diagrams, if I remember correctly. So let's say we got a box, right? And this box is on wheels. So we got a roller box. So this box is moving forward. Let's say it's moving forward at a rate of 3 miles per hour. So 3 miles per hour. So the box is going decently slow. But let's say the box suddenly is going to get pushed. So there's a guy right here, and he is now pushing this box. And he's pushing on this box at a rate of, let's say, 2 miles per hour. So there is two things acting on this object. There is the guy who's pushing it, and there is, of course, the box's own speed. These two things are acting against one another. So now in physics, and for people who are in physics, and if I'm doing this incorrectly, my sincerest apologies. This is just an example of a free body diagram. These are probably going to be forces because it has mass behind it, but we're just talking about how these can be written so that they cancel. So obviously, we're going to treat the box's forward direction as a positive 3 miles per hour, and we're going to treat the guy trying to stop it as a negative 2 miles per hour. So this only happens because we have direction. So direction. So you can't have positive and negative without direction to work with. So let me give you another example of why we need direction in order to make this work. So let's say instead we have a guy standing in the middle of the field. So this guy is right here. So he's right there. And let's say he moves up at a particular speed. So it goes whoosh. So that was pretty fast, right? So it goes whoosh. So his speed is pretty fast. So we'll say it's pretty fast. So if he's up here and he moves down that fast, well, there's no negative speed here. There's only positive speed. He's only going faster and faster. So if there's no direction, if I just tell you his speed is 3 miles per hour, which way is he going? Well, I didn't tell you, so you don't know. So if he's going 3 miles an hour and something hits him going 2 miles an hour, will he be going faster or slower? Well, let's say this object is like this. Well, which way are they going? Which way are they going when they hit? Because, just because it's right there right now doesn't mean it'll be right there when they hit. It might be over here when they hit, or it might be over here. It might be way up here. The direction is very important. This is why vectors require direction. So vectors require direction. So direction is very, very important. And the way that vectors normally will write their direction will be very familiar to you. So usually, let's say 3 miles an hour going this way. Let's say this one's going 2 miles an hour that way. So if this is 2 and that's 3. So, okay, so now we understand which way things are moving. When this one hits that one, it's probably going to get locked a little off course in that direction once they actually hit. So now that we know the directions that they're going to be hitting, we can describe some of these positive and negative. So this guy's probably moving negative in the X direction. So it has a negative X direction. Meanwhile, this guy has a positive X direction. Both of them have a positive Y direction because both of them are going up. So now we're able to look at this in terms of X and Y. Okay, so this is moving this far to the left, that far up. Great, this one's moving this far to the right, that far up. Which might sound familiar because this is how we talk about things like slope and things on a coordinate grid. We talk about them in their terms of X and Y. And so vectors can actually be written in terms of X and Y. So we're going to look at how that works in our next little demonstration here. So let's go back to this over here. So we're going to talk about vector addition and subtraction. So vectors are written in component forms. We talked about this a little earlier. So just a reminder, component form just means you write the vector in how far it's moving on X, how far it's moving on Y. So quick reminder for that. Let's go back to the board. So if we have a vector, and that vector is equal to 3, 4, what that means is moving 3 forward and 4 up. So if we draw the grid that it's on, and we say that it's right here, 1, 2, 3, 1, 2, 3, 4. So this vector is moving from the center up to here. Now it doesn't have to be on the center when it starts. It just needs to have the movement that matches that amount. So it doesn't matter if the vector's here, 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 or here. These would all be represented by V. So we're just moving 3 to the right and 4 up. As long as it's doing that, it can be representative of V. So real quick, let's go ahead and erase this and let's talk about vector addition now. So vector addition, when it comes to component forms, it's very straightforward. All you do is you add the amount of X's to X's and Y's to Y's. So to give you a demonstration of that. So V, we know, is 3 to the right and 4 up. So let's write another one. Let's call this one U. So we have a director U and director V. Oh, I'm sorry, vector U and vector V. I don't know why I said director. So we have vector V and vector U. So let's say vector U is -2 and a +3. So if we were to write vector U all by itself, vector U goes to the left and 3 up. So 1, 2, 3. So vector U does that on its own. So if that's U, this would be V. So now we're going to talk about what happens when we do U plus V. I'll do this one in pink. So let's say we have U plus V. So if we have U plus V, all we're going to do is we're just going to add the values of those vectors. So 3 plus -2 is a +1. And 4 plus 3 is 7. So we go forward 1 and up 7. So we're about, actually, we should be a bit taller. Let me rewrite that. So we go up 7. So we're up there. And so real quick, if we were to take the V that we have over here, and we were to write it on the edge of U, then we would point, oh, well, would you look at that? So if we do U plus V, it literally is just what would happen if we put one of these vectors on top of the other. And so does it work the other way around? Well, if we try it, yeah, it turns out it does. So adding vectors is the same as just kind of stacking them on top of each other. And this would work no matter what the vectors are. And this is why addition works the same, you know, plus or minus, or I'm sorry, not plus or minus. When you add them, it doesn't matter if you add the U's first, or if you had, or the X's first, or then you add the Y's, or if you had the Y's and then you add the X's. As long as you line up your X and Y values, you'll be able to add the vectors together. And the same is true of subtraction. So let's go ahead and do some subtraction now. And I'll get a visual for subtraction. So this time, let's go ahead and do subtraction in blue so that we have some different colors. So let's say we have V minus U. Sorry, I don't know why I wrote that equal sign. So we'll have V minus U. We'll go ahead and draw that over here. So what V minus U looks like is, so basically, so we're going to start off with V. So V does this. And we know that U does this. So this is the way, this is the way that U normally goes. So whenever you subtract U, U actually does the opposite of what it normally does. So this minus U means that instead of going left and up, we're going to go right and down. So we're going to do the same thing, but in the opposite direction. We're going to put that over here. So now we're actually going to be further to the right than we started. So this blue one is actually going to go much further right, but it's not going to go as high. So let's see how that plays out in the math. So we're doing 3 minus negative 2. So when you subtract a negative, subtracting a negative is same as adding. So 3 plus 2, that's going to be 5. Okay, and then 4 minus 3. So 4 minus 3, that's going to be 1. So, okay, yeah, it was exactly what we expected. It goes further to the right, but it doesn't go up quite as far because we're subtracting what we would normally be adding. So remember, when you subtract vectors, that if you're subtracting a negative, that's the same as adding. And when you're subtracting a positive number, then nothing changes, just normal subtraction. So this is how vector addition and subtraction works. Go ahead and practice a couple of these, and I'm going to show you one here on screen in just a second that I want you to go ahead and practice. But this is a pretty straightforward process. As far as vectors are concerned, adding and subtracting is a pretty simple process. So we're going to go ahead and go back. So now we're here. So we talked about vector addition and subtraction. And yeah, so now this is the one. So you're going to have to both write the vector and you're going to try to add them yourself. And of course, I'll go over this in the synchronous hours, but I want you to go ahead, try it for yourself. I want you to treat north as going up. So north is like the positive x value, and south is like the not the positive x value, I'm sorry. North is the positive y value, and south is the negative y value. Meanwhile, east and west, east is going to be the positive x value because east is typically the right if you're facing north. And west is going to be the negative x value because, again, if you're facing north, west is usually on your left. And of course, you don't have to get all that done today. We'll go over it in the synchronous hours, but these are going to be the things we're going to be over. We'll have some more examples. Go ahead and try out the independent practice, and you have a great day, and I will see you in the next one. Bye-bye.